computing more than 30 years. And he's the principal investigator, PI, for a number of NSF supercomputers, including the current Frontera systems, which is one of the largest systems in the open science research, which is the fastest supercomputer, and is also leading the next NSF leadership class computing facility. I'm sure his talk will cover that. So that is the leadership class computing, which will be the open science again, not the DOE and other, but from the NSF. And he received his bachelor's degree in electrical engineering and his master's degree and doctorate in the computer engineering from Clemson University. And I recollect, Dan, I think we met when you were in, not at TAC, I think you were in the C plant project, am I right? Yes. So since that time, I don't know how many years it has been, I think.
Started on that in 2006.
2006. So 19 years. So that's how I got introduced to Dan when he was at doing the C plant project. And since then, we have been working, collaborating a lot for last 19 years. So let's give a big welcome to.
Need that one. Thank you very much. Yeah, and I think we've been working together for about 19 years, but originally I read your papers when I was a grad student, so that just proves that you're actually older than me, which is impressive, because that photo was from a really long time ago.
I didn't know that.
The hair color was not all Photoshop back then. There it is. Awesome. Excellent. Thank you very much. Yeah, and thank you not only for the invitation for the 8th, 9th, 10th time to come up here, but for the long partnership and friendship we've had. I have a slide on that, but it's been super important, and apparently I have an outline slide that doesn't apply. I did try to have less slides this year, so I actually finished in time to take some questions, but I think I only succeeded in making the slides denser, so we'll see if I actually finish on time. And I did try to do new stuff. Wait. Apparently not, because that's last year's. May I switch to the laptop? So, yeah, that was a good talk too, but it had lots of slides. I'm going to harken back to it a couple times, but yeah. Is that going to screw up the online stuff?
People can.
Good thing I have less slides.
Talk last year if you missed.
Yeah. And I have new graphics. Change the slide template. Yeah, just right there. Yeah. There we go. Start mirroring. Do not set up a keyboard. Slideshow.
Okay.
Perfect. All right. Now you get to see all the interruptions and stuff's probably going to do in the middle of this. So because as usual, we just got a set of questions that's due at noon that came in this morning, which only happens twice a week. So yeah, updated TAC graphics from last year. That's part of it for Horizon and the leadership facility. And yeah, so hopefully updated messages. But if you haven't heard me talk many times before, apologies to Samir and DK and Keith and people who've heard me speak dozens of times. But let me tell you just quickly in 2 slides a little about TAC. And we'll get into the new stuff, but we're, not only the UT Austin research computing facility, but much like the Ohio Supercomputing Center here, we have a broader mandate to deal with the state and then through federal funding to deal with everybody. So we have users from almost every academic institution at R1 and then many R2s. I think we have 450 institutions who currently use the systems in the US. Again, we're primarily supported by the National Science Foundation, although we have work with 6 other federal agencies. We have a team of almost 200, and we have lots of machines. We put out millions of jobs per year, billions of core hours, increasingly GPUs. And from a pretty substantial federal investment, I went back we actually audited the user database last year. So we've had about 125,000 users come through the system since we started in 2001. 90,000 plus of those are grad students. So if you're a grad student, hopefully you've gotten to use our systems. We run into random people. We had a call with people doing file system for XAI the other day, and they were like, oh yeah, we all use Stampede for our master's thesis. So that was good to hear. But again, thousands of projects per year. We've had 4 Nobel Prize winners use the systems for part of their research. Most recently, David Baker, who won last year, who's been a user since 2007, I think, on our boxes. Minnie Gordon Bells, all sorts of leadership type computing. And most of our time we give away, which people don't understand, but the NSF or somebody else pays for it. And it's free to the end users. So it's through the NSF Access and the NSF Leadership Computing Program, now through the NAIR, the pilot, the National AI Research Resource, and then there's various other programs for Texas folks that we put through. And as I mentioned in all of these talks, and this slide would have been in last year's too, but it's hard for me to overstate how important it's been to have the partnership with MVAPICH through the years. It's been part of the stack on every system we've done, going back to Ranger, our big AMD system in 2007. Whether we have an Intel system, an AMD system, an NVIDIA system, whether it's a CPU system or a GPU system, we build MVAPICH for it. And there's a number of reasons for that, but sort of our core strategy for every system is to always have 2 compilers and 2 MPI stacks and build all the applications against all of those, because then you sort of know whose fault it is, for the most part, right? That's the ultimate goal is, well, is it the compiler? Is it MPI? Is it the user code? Is it some other library? And if you have multiple implementations, it's amazing how many problems you can find. But it's often also our best implementation. So through this very long partnership, where we've had multiple people who've come through the team here at Ohio State, end up on the team at TAC. Amit's here today, his postdoc here before coming down and joining us about 8 years ago, 6 years ago, I guess. But Jerome Bien before that did a postdoc here, came down to TAC. So spent many years with us. But we get a tuned stack for all of our systems. This year we've worked a lot on Vista. The team's given us a new build for Grace Hopper and the sort of unified memory integrated CPU, GPU. We get a lot of early insight into potential issues with the interconnect that we're using at the time. It's been mostly InfiniBand, but there's been a few other things in and out. Some OmniPath. We just put in OmniPath 400 on some of it. So, but we get to keep our vendors honest, and we get an incredible tool for debugging, and an incredible support team when we have a problem we can't figure out, to come up here. And again, so many students on the team through the years have made a big difference in how so many of the big systems have worked. So I think, yeah, if you go back to Ranger, that's also 19 years that our team, you've been working with TAC. You're funded partners in the leadership facility and through the lifetime of the leadership facility, and we hope that goes on forever. So we do run a variety of systems, and I'm going to talk mostly about the next one, obviously, Horizon, and issues that I see coming down the pipe, but right now we still run Frontera, which is sort of our venerable system from 2019. It's getting a little long in the tooth. We're actually starting, we're like 6 years and 3 months of production on that, so we're into year 7. It was mostly a CPU-based system with almost 500,000 cores. About 8,400 nodes. We have an AMD-based system with a bunch of NVIDIA A100 GPUs in Lone Star. That's sort of a little more of the Texas system. We have Stampede 3, which is the Sapphire Rapids. It now also has some H100 nodes in addition to the Ponte Vecchio. But Sapphire Rapids HBM, that's sort of the broad mission access system for the NSF Access program. We just had a site review for the first year of operations on that last week. We have Vista, which is sort of our bridge system to the next generation. It has 600 Grace Hopper nodes and a couple hundred Grace nodes, the pure ARM CPU. So it's our first ARM system in a long time. Well, really ever for double precision. But it's been in production for about a year. As we get ready for Horizon, the one I'm going to talk about, we'll have 4,000 Blackwell GPUs and another almost 5,000 Vera, the next generation after Grace, ARM nodes on it. So that one's coming down the pipe. It'll require a new building because it's going to end up at a peak of probably around 12 or 13 megawatts when all is said and done. But the existing big platforms, we have a peak power in the data center of around 9.5 megawatts. Our average daily power is about 6 megawatts plus cooling power. And we have a bunch of smaller platforms that live in there too. We work with Indiana University on the Jetstream system. We have a little bit of the hardware, most of it's at IU. We work with University of Chicago and Argonne on the Chameleon computer science testbed system, cloud testbed system. We actually have most of the hardware for that one at this point. We have an AI inference platform. We run with Sambanova. We have some in-house things, our Kubernetes clusters, and then various storage platforms that many of you use, Ranch Corral, Stockyard, for the different layers of storage. But we are expanding out through the leadership facility. This project actually got its start about 13 months ago now, a year ago July, through the very creaky, long and complicated federal budget process, which has been an adventure this year, but we move on. Some on that on the next slide. So, but the job is to replace Frontera with something that does sort of 10x the science. We'll talk about how we got to those metrics. But the idea is that the facility, whether it's attacked or eventually gets renewed somewhere else, we don't intend to let that happen, but it's always possible, will be a more sort of long-term footprint. We have, in fact, we're working on a report right now with like the next generation very large array. And the problem with the old model of doing systems is you sort of win a grant and you put up a system, it's in production for 4 or 5 years, and then it goes away. The very large array, we're in planning with them now. They'll have the first antennas up in 2030. They hit full data rate in 2037, and then they take data through 2057, right? So we're looking at 30-year planning horizons for the big instruments. And to say you're going to do your processing on a system that there's no guarantee will exist 3 years from now is a big problem for some of these larger projects that need to make big commitments around data sustainability and how they're going to get their analysis done. So the idea of the LCCF is we'll be sort of on the same timeline as a lot of the big scientific instruments. In fact, we're in construction now. We should hit production by definition of their operations. The systems will be sooner, but in 2027, and then there's a potential 10 years plus a 10-year renewal option for operations. So the hardware will obviously have to change out a few times, but the idea is the facility will run through 2047. So we're looking at a fairly long period. The biggest thing we need is more power to deal with this. That's one of the big challenges I'll talk about very briefly, but so we're building with a new facility that is the actual building, not a mock-up anymore, of SABI data centers. We're sort of the left-hand side of that building. And we're, raised floor goes in October. So we're getting really close to the end on the build out there. But we'll have 15 megawatts there with the option to go to 20. The substation there is actually 85. And the primitive customers on the other side, we're supposed to use 3 megawatts and, of course, switch to AI racks and are at 9, but there's still plenty left. Although another building will go where there's green space. There's probably going to be another data center. I think that's true everywhere in the world right now. So that's the plan. We are, trying to do a multi-year long-term construction project with commitments to vendors for big systems in a version of the federal government where they pass continuing resolutions that last for 90 days over and over again and have no continuity from one year to the next. So that's fun. In fact, my 7 a.m. question from NSF today was about 3 versions of continuing resolutions starting in October. So, but we are fully funded in the fiscal year 26 president's budget. There was much lobbying activity, but not that we can do lobbying, federal advocacy activity. Lobbying would, of course, be illegal. We're not entirely sure how we got in a full funding in the president's budget because we're the only large NSF project that did. But we have the same level of funding in the Senate draft of the budget and the same level of funding in the House draft of the budget. So believe it or not, even with all 3 of them at the same starting point, there's still plenty of ways for them to screw that up in negotiations. But we'd be happy with any of those 3 numbers because they're all the same or anywhere in between. So we're pretty optimistic that when the negotiations finally settle, theoretically by October 1st, practically by next March, that we should be in good shape to keep moving. So, yeah, and this is the big year for construction because we have to pay for the end of the data center and the compute systems. We have 201 million in the budget. It's a big number with a big target bullseye on it in the budget. So in the president's budget, it's 5.5% of the entire NSF budget, which is more a comment on how bad the NSF budget's doing than on how well we're doing. But fortunately, in the Senate budget, it's back to its more reasonable 2%, even though it's the same number. So let's talk about the system and then interesting things moving forward. So the plan, and this is actually happening at this point because it's too late to get out of it, but the accelerated part will have 2,000 of the Grace Blackwell modules. And if you've seen the sort of NVIDIA packaging on this, it's one Grace CPU chip with 2 GPUs on sort of a daughter board that lives in the node. So I'm saying it's 2,000 nodes because that's how we're going to treat them the way that the vendors are building them. It's 1,000 1U shelves, and there's a chip-to-chip connection in there because we're putting network on the PCI complex of each CPU. We're probably just going to drop VMs on them and treat it as 2,000 nodes, but it's 1,000 nodes or 2,000 nodes for your vendor definition or less if you do NVL72. And but either way, it's 4,000 GPUs. There's an 800 gigabit InfiniBand and a non-blocking fat tree for each Grace Blackwell board. so 2,800 gigabit ports. Again, 4,750 Vera nodes. Those are come in about 176 cores apiece. We did 400 gigabit InfiniBand, also a non-blocking fat tree there. More on the fabric in a second. And again, you see the precision numbers, which are, actually all of our benchmark apps are coming in between 15 and 20. There's one that's much higher because of an algorithmic change. One is a little bit lower, but still around 9. So for true double precision, 10 to 15x for most of the apps, because these lower precisions didn't exist in a functional way when Frontera went up in 2019. It's hundreds of times faster, but sort of 20 exaflops at bfloat 16. So it's a fairly nice AI system as well. We're also doing a lot of changes to the storage. First of all, no spinning disk, because I tell people I got my first spinning hard drive exactly 40 years ago in 1985, and I was very excited to get my first hard drive and move off floppy disks and cassette tapes and stuff like that in 1985. I'm equally excited to see hard drives go away in 2025 as rebuild times are going through the roof on 30 terabyte drives. Once you're down to do a rebuild, it's 30 plus hours to get the drive back running again. So, and it turns out when you fail a drive and start rebuilding, you're putting stress on that declustered RAID group, and it's the most likely time to see a second and a third failure in the group, and then you rebuild for days at degraded mode. So it's can't wait to see all that go away. But yeah, so part of it is we're going to all solid state at a write speed of 8 terabytes a second. So read speed of 16 terabytes a second. Hopefully we'll end up around 400 petabytes usable. There's so much volatility in the flash market. I'm not sure exactly where that's going to land. But we're also using VAST, which is sort of a different approach, a lot more client-side caching than the traditional parallel file systems we use. If you're doing really traditional large-scale HPC, where you have a giant HDF5 file that 100,000 processes are talking to, and they're doing overlapping access to regions, it's not quite as fast as Lustre in those situations. But if you're doing what users actually do, which is file per process and 90,000 Python conda installs and builds in front of everything and 1 million AI containers and tons of little I/O, it is vastly more, no pun intended, more resilient that we found that Lustre. So we're trading a little bit of performance for not getting up at 2 in the morning to fix the file system twice a week. So we'll say, knock on podium, that we have a VAST cluster that's supporting Vista and Stampede 3 that's been up since February of 2024 without an interruption. So, which is terrifying because that means there's a failure mode that I don't know about yet that's still coming, but the resilience has been remarkable. We're still looking for sort of depth storage. It may be some other file systems for high performance, but I mean for high capacity with more modest performance, but this will be sort of the front end, will be vast. So this being a network software conference, primarily, let me say a little bit more about the network. So as I mentioned, we have a non-blocking fat tree for the GPU nodes. We have a non-blocking fat tree for the CPU nodes. But they're separate trees because we don't see the need for full non-blocking beyond that. The case where somebody might span CPU nodes and GPU nodes is mostly theoretical. Like we've never had a user run a job that crosses node types in the last 30 million jobs that we've run. So realistically, we don't see anybody running between them in a single job. So unless people want to get creative on a top 500 run, but nothing important should run that spans those trees. So we have another layer of the network that will be much more, sort of, we're doing like 10, 11 terabytes per second up from each of those trees to a core network that then also bridges in the storage, which again, we need about 20 terabytes a second out to the storage. Projected bandwidth is 16. You need more network than that to actually achieve that, right? So, we have about another 800 ports to get enough storage nodes at 400 gigabits to hit the performance. Yeah, interesting thing about the system is when you start counting cores and what the total performance is. I don't normally count this, but there's likely to be there's 728 of those C nodes coming in, each of which has a 96 core processor on it. So, and then there's another 300 that are actually on the flash arrays. But but yeah, order 90,000 cores of that probably mostly don't do anything because you can run the file system on 8 or 16 cores. So, I'm having horrible, stupid thoughts about creating like a 64K throughput queue that actually runs on the storage nodes because it seems a shame to waste 70 or 80,000 cores over there. Again, 20 terabytes a second to the storage. There's another actual backend IB network between the front end servers and the back end servers that adds again over 1,000 nodes. So we end up with about 9,000 endpoints, 15,000 cables. The sort of unreadable figure for the network should end up looking something like this. We found a lot of fun in what you can plug into what between NDR and XDR and between by 4s and by 2s. And we actually did, when I get NVIDIA to change the roadmap once on which splitters they were going to make and what ports, when I pointed out that they could make the change they were talking about, but I was going to pay the same amount and it was going to cost them $11 million. So but yeah, so essentially 66 racks with the QM3200s, which are the 400 gig switches. That's the big CPU port, 66 racks of that. There's 28 of the GPU racks. By the way, those 28 racks, even though there's only 28 of them, they are 230 kilowatts apiece. With 144 GPUs per rack, I think 1,200 liters per minute of flow for coolant through them. So there's 28 cabinets, but they're most of the infrastructure because, again, you're at 2.3 megawatts per 10 cabinets, right? So that's about 6 megawatts of GPU in that fairly small footprint. And then there's another 28 racks over there for the storage system that's in the previous generation because that's all that's qualified in the storage nodes, so the different color links, and then all into the QM3400 cores there, if you know your InfiniBand. But again, it's sort of 58 terabytes per second per leaf in the GPU side. So in those trees, we're non-blocking. We have a very rich fabric, 28 terabytes per leaf on the CPU side. But then only about 20 terabytes a second between the file systems and the compute at the core, because we just don't see the need to populate the rest. And I would be remiss, we'll come back on some network issues, but that's basically the topology. I would be remiss in not finishing out my discussion of the LCCF by mentioning that we do have a bunch of partners around the country. DK's group and OSU remains a partner on the software side and Cornell on the training side. But then we have 4 sites where we're putting additional hardware that are distributed centers. The 3 that you're probably not surprised by, each of which has their own sort of lane in this. NCSA at Illinois is doing quantum accelerator testbed, but also looking at particularly I/O and accelerated workloads, I/O for GPUs. PSC is going to do a data mirror for us and focus on sort of fair access, protected data, the sort of data sharing aspects of a lot of this. At Pittsburgh, San Diego is doing test beds on sort of a subset of science cases, looking at machine learning inference for high throughput scientific workflow. Open Science Grid is headquartered there, so Large Hadron Collider comes to mind as something where they'd want to do inference at large streaming scale. And again, exabyte size instrument workflows. And of course the PathOSG stuff. And then AUCC is the Atlanta University College Consortium or Center Consortium, which is doing workforce related stuff. It's the coalition. The machine will actually sit at Morehouse, but the coalition of the HBCUs in Atlanta and the HBCU Medical School that's there. So that's sort of build curriculum, broad data science, get things out in more hands. Again, we did sort of an early system for Horizon that was Vista that I've mentioned. It went into production last summer, so it's given us a year on this sort of unified memory platform, tightly integrated CPU, GPU. And what we thought would be the big issue, which was moving to ARM. Moving to ARM has been surprisingly painless. The compilers are fairly mature. If you're using x86 specific intrinsics, you might have to make a change or two, but literally we had 21 benchmark codes we were trying to bring up from the mostly big shared well-known science codes, and hundreds of thousands of line of software that I used to think was horrible until I learned about AI software, and then I've decided all the scientific software is robust and mature. But they all just built basically out of the box. We had every single one running within 2 months. Obviously, still performance tuning going on. We're a little behind on, and Samir can probably say more about this and will fix it for me one day, but performance tools in the space. Actually, Samir built the entire E4S stack and put it out in SPAC packages on Vista, so it's all sitting there on the file system if you want to use that. So the only thing we're a little behind on is sort of Grace Hopper integrated performance profiling tools. But the ARM part has been really nice. And again, it uses VAST. It's using 200 gigabit InfiniBand to the CPUs, 400 gig to the GPUs, so 1 generation early. But it's done super well. I think I showed some early performance from it last year. Then it's improved slightly, but still basically a really good story since then. We have actually started putting in some LCCF hardware because Horizon's now going in that new data center in Round Rock. We're putting the archive in what is the primary TAC data center now. We have an old TAC data center. We've been storing our archive in, but if you've ever used $archive at TAC, commonly known as Ranch, you've written to one of the Ranch tape archives. We've had a version of it since 1986 that has been around. So this is, I think, the 9th set of hardware or something like that. But that's the new Ranch, came into the data center in June. We've moved a few petabytes to it. It's doing pretty well. In fact, we just finished copying the 5 petabytes of the IceCube neutrino data set over to it. But it's now, if you've been to TAC, where the main data center is, I just show it because it has really good front panels, where Corral used to sit. Yeah, we're bringing those tape archives up. And again, we'll probably open it up to users to migrate your archive stuff in the September timeframe. And per normal, you'll have like a year to copy stuff over because we have order 150 petabytes on the old Ranch. And it takes a while, but that'll shut down in a year or two. So that's the LCCF. And so I want to now take some time to complain about what's coming down the pipe and issues that I see that are making our life difficult in trying to sort of optimally use and optimize in general code and applications on these things, particularly with regards to the network. All the stuff I said we should do last year, we still need to do. So I'll come back and revisit that briefly. But before I get into the rants, let me say that in some extent, we're in a bit of a golden age, right, for what we're doing. The next slide's titled The AI Disruption, and what it screwed up for us. But at the same time, it's put a vast amount of money and interest into what we do. And I think it's validated a lot of the work that we've done in HPC, particularly on the network side, right? Everybody believes that we need high bandwidth, low latency networks. If you talk to the cloud providers 10 years ago, they were saying, you guys don't need those networks. Why are you spending the money? Just come use the cloud. Now they're like, we have much faster networks. Come use us. After Microsoft put in, order 30,000 miles of InfiniBand last year. So we had 200 miles of InfiniBand. We used to be one of their biggest customers. Now we're not even close. So we're a little blip in that space. So, but again, it's validated a lot of what we've done. It's obviously driven costs up. But but there's, spending on multiple networks, spending on multiple chips. There's sort of a renaissance in architecture. There's a lot of good stuff going on. So I don't mean this to be a rant against everything's happening for mostly reasonable reasons, except the ridiculous data center push. But but at the same time, the rapid change brings lots of consternation. So this is just sort of my list of issues. And let me start this by saying AI has been a huge disruptor, and things that we struggle with that I'm not going to really talk about is how much of simulations we should replace with surrogate models and at what precision. It's clear that it's going to be some of it. It's clear it's not going to be all of it. Where that slider bar fits is a huge debate right now, and I'm not the best person to talk about it, so I'm really not, but that's going on. Certainly, even if you leave the core simulations in place, you're probably going to organize all the data for them through AI, and you're probably going to do all your literature searches with AI. So it's probable that it's going to be a huge disruptor in the overall science workflow, even if it doesn't replace your core simulation, or it might just change your core simulation. But the thing that is not disputable is that it has disrupted the marketplace in a huge way, right? So because there's $400 billion in spend this year in AI infrastructure, which is 40 times larger than HPC has ever been, and larger than the whole server market globally was in 2020. So it's created lots and lots of changes. So all of this is with a view on what that means for us as we look at sort of things being built for the AI market in our space. So so some issues I want to just dive into a little bit on, and then I'll just recap the other ones that I don't have time to talk about. But nodes are fatter, which means we have a lot more compute hardware there, and they're a lot more performant, but there's a lot more stuff in them and a lot more complexity, and they cost a lot more, and that has a lot of implications for us. We have lots more network paths in both kind and quantity. So we have different types of network. We have multiple paths in and out. We have a lot more networking software options, because what we really need is 16 different ways to do a broadcast. But we have unified memory, which gives us a simpler programming model from both AMD and NVIDIA. But optimization can be a lot harder, particularly if you want to get fast, low latency messages out of the network. So I'll drill in just a little bit on each of those. So the thing that I struggle with for a number of reasons is, yes, we can pack a lot more into a node, but that makes them more expensive and makes allocation a bigger problem of them, right? So I just said, and we've gotten some ridiculous deals on pricing through the years, but if I go back the 19 years to 2006, we started working on MVAPITCH, right? We did Ranger that year, where we were doing quad socket AMD nodes. If you just divide the system price by the number of nodes, so this is all in network, storage, everything, not the actual price per node. But for a quad socket node, we were spending about $7,600 a piece, $2,000 per processor socket, right? So Stampede, and there was some Xeon Phi fun there that Intel made us a deal, but divide system price by node, it was 6,400 dual socket nodes, $5,000 a node, still roughly $2,000 per processing socket, 5 years, 6 years later, 3 Moore's Law iterations, everything much faster. Stampede 2, same story, 5 years later, much faster. It was about $5,000 a node. This was in the Knights Landing era, so we had a fair number of single socket Knights Landing nodes and then some dual socket Skylake nodes. Still running those Skylake nodes, by the way. but power had gone up. But because some of them were single socket, I was looking at like $3,500 per socket, but still about $5,000 a node, right? So we've been in that dual socket nodes around $5,000 for 15 years. Frontera, it started to go up. Again, 3.5K per socket on straight dual socket nodes. There's about 8,000 dual socket nodes, still about $7,300 a node. So 5 to 7, and there's no way we were going to ever replicate the pricing deals we managed to cut on Stampede and Stampede 2, but call it $7-8 a node in sort of typical HPC applications, 2006 to 2019. If you go price out an NVL72 rack, the NVIDIA, I'm sure we're going to hear more about these in some of the other talks today, but the 72 GPUs all linked via NVLink into a shared memory space, which they're selling ridiculous numbers of. CoreWeave is buying them as fast as they can take delivery, $3 billion a quarter worth or something. So the price per node, where the node is that 1U dual socket quad GPU shelf, it's about $200,000. Get them for 3.5 million if you're pretty aggressive about it. The list is like 5 million a rack. So you can call that $100,000 per CPU socket. But suffice to say, that's a significant departure from where we were the previous 15 years in that. So, and yes, they do a ton more. There's 4 Blackwells in there. The total computation is ridiculously higher, but we still sort of allocate on a node basis. So let's think about the implications of having node prices go up like 30x in 5 years for the price of a node, right? So first of all, in case you haven't noticed, government funding for higher ed and open science in general, probably not on a fast increasing curve at the moment in years. Just whether it's how apocalyptic becomes the question. So systems are going to get a lot smaller in nodes, and you already see things that used to be, buying a 128 node cluster, they now buy a DGX box, right, or 2. And whether you get the 2 versions of Blackwell that ultimately will be available, Horizon's going to be in the NVL4, the 4-way NVL linked, or the NVL72 that they're selling now. Your basic hardware node is 2 boards, each with a Grayson 2 Blackwells. It'll be 4 GPUs per board in Rubin, so you'll have 8-way nodes. We're going to treat that as 2 nodes, but you talk to a Dell or Quanta or Supermicro or anybody building them, that's a node at this point. And although they have much, much more capacity, if you have a multi-node application, your basic allocation unit remains a node. And sure, we can put a bunch of VMs on a node, or you can use various kernel limits to share them, run AI, does some nice GPU sharing if you don't let users specify how many they want. You can put a bunch of containers on them. There's a whole bunch of things you can do, but all those involve sharing something physically, right? If you have 10 containers, you still maybe have those 10 containers talking to one network card or to a fixed amount of memory. Or increasingly, you're in a capped power environment, right? So the maximum power we can run to a Grace 2 Blackwell board, I believe it's 2,700 watts at the moment, right? But that's less than the cap for all 3 of those chips, right? If you ran them all at max. So somewhere you're regulating power. And so how do you optimize MPI performance if you're on a node with 8 containers running and you only see one of them and you have no idea what the other 7 are doing, either on the network or in terms of how much power they're consuming, or how they're talking to the one shared set of storage that you have. We could limit each of them through QoS mechanisms that we don't really have exposable to users and use much, but theoretically they exist. Say everybody gets 1/8 the bandwidth, but then half the time you won't be using most of the bandwidth on those nodes, where you could maybe give one container half if it needs it. Some other container uses more power, yours slows down, your performance isn't repeatable, right? So there's a lot of new mechanisms in network. I suspect we'll hear some talks about this to be able to support lots of containers and lots of channels. And the protocols are increasingly built for this, but you're still physically sharing stuff. And it's awfully hard to tune performance if you only have a virtual slice of the node and somebody else has most of it. So, but a lot of things that used to be, we were buying a 512 node cluster are about to becoming, we're buying a 32 node cluster or less. And we're really not ready from that from a scheduling perspective, from a quality of service perspective, from a power management perspective. And because the easiest thing to do is just give everybody a node when they run, or have shared nodes where you get random and non-reproducible times. wait times are likely to go up pretty substantially as a result of that. So that's raising nodes costs. Let's assume you can afford these nodes, and let's talk about the network. And so I'm only slightly violating some NDAs here. But let's talk without violating an NDA or two. So this is a sort of typical NVL node, sort of the NVIDIA recommendation for a box. And again, you can go to multiple vendors and get versions of this. And this is sort of, I've deleted a few things because this is sort of the common denominator. So if you go through and look one of these dual Grace Blackwell nodes, you have 11 network interfaces per node, right? Because you have on the back end of the GPUs over there, you have your 4 NVLinks, right? Which are only go to the scope of that rack, right? So that's a network that has 72 endpoints, whereas your other networks might have more. It's 1.8 terabytes a second, which is ridiculous when you think about it, right? Versus the 400 gigabits, that's what, 32 times faster than your InfiniBand link. But it's also a big, thick cable with a lot of parallel copper strands to make that work. There's 9U of switch and cable management in the rack just to deal with 18 of these shelves. But you have your 4 NVLinks, then you have all those things labeled CX7 or your InfiniBand connections. There's 2 on each board, so there's 4 of those. So that takes you to 8. There's also 2 DPUs to manage the local storage. The Bluefield 3 cards here are your 200 gigabit InfiniBand, so there's actually 4 external ports, but it's 2 cards. So that takes you to 10, and then you have your management Ethernet out the front end, gives you 11, which of course goes across those nodes, right? So that's your off-node network. It's also your GPU to GPU path on node. But if you want to just make life more fun, you also have your link between the CPUs, your 300 gigabyte per second. It's on a by 12 PCI lanes to the Graces that link the 2 boards together from the CPU perspective. And then you have your C2C links, which are NVLink, but not the same NVLink at a different speed, where you have channels 2 each from the CPUs to the GPUs. So we have lots of kinds of network at lots of different speeds and lots of paths on this node. So start thinking about, so again, 11 interfaces, 4 different speeds and 4 different latencies, just because of the type of network in the card. You have no idea what the InfiniBand topology is and how many more different latencies you have between racks and things like that, right? Think about what it's like to set up optimal routing of messages in that environment when that's 1 node in your 18-node rack and potentially a multi-rack environment. What are the odds that a user is going to grab a random Python container out of the cloud that they run them all from and pick the correct network to run across on the first try? The hint is, right now, when we have 2 choices of network and you can run over InfiniBand and Ethernet, their hit rate is near 0 on picking the right one. They almost always start with the wrong network to run. When you have this many choices, the odds of it being optimal out of the box become very, very low. And things that involve users doing tuning, if you've run a shared system, you know the hopelessness of that statement and the void of futility you're looking into when you talk about user-based tuning. So so these things are damn complicated, right? And then of course, yeah, I don't think I got into the combinatorics here, but yeah, so we also have theoretically unified memory. And again, from a programming model perspective, even from performance on a lot of things, it is a wonderful thing and it's a great feature and we want to have it. And both on like the APUs on El Capitan from AMD, and then with the Grace Hoppers and now the Grace Blackwells, we're seeing this from NVIDIA. But we all know that for really good performance, well, we all know in the system software community here that actually knowing where your data is key to reducing the number of copies, to getting good transfer rates, to do all those things. And again, there are network stacks coming down the pipe. We're going to hear some of them today where you get great transfer rates because they've optimized this, but all those people know where it is and how to manage that, right? So in the node on the previous slide, you have 1 address space, but you have 2 physically separate LPDDR memories and 4 physically separate HBM memories on those GPUs. So you have 6 memory spaces where data can potentially reside. And again, depending on your path through whatever set of buses and links to whatever network you have lots of different latencies, right? So if we sort of oversimplify, but on old GPU nodes, the kind that we've used for the last 10 years, right? You have data in CPU memory or GPU memory. And yeah, there's other complexity. One CPU is probably directly connected to the PCI bus where the NIC is, and the other one is not, and there's some asymmetry there. But you more or less either send your message from CPU memory, or you can do GPU direct, copy it right over the PCI bus to the NIC, right? That was the old days. You had, sort of a couple of options to think about. Now, your data is sitting on one of 6 memory locations on the node. You can message over NVLink or IB. And let's just think about messaging and none of the other kinds of communication to storage or anything else, right? So which is better for a small message or like a barrier? Do you send it over the NVLink from the CPU memory or sending it over IB from the CPU memory, where you have one less copy? Or do you stage from the CPU to the GPU and then use NVLink, or do you stage from GPU to CPU and then use IB? Oh, wait, there's different sets of nodes you can talk to depending on whether you're talking over the IB or the NVLink. So the destination of the message will affect which one of those you do, whether you're in rack or out of rack. But of course, the in rack for the NVLink is not the same as the top of rack for the IB switching, because with that many IB ports in a rack, you need at least 2 switches. So what's on the local switch for NVLink and what's on the local switch for IB isn't going to matter. If you pick the InfiniBand link, which one do you use of the 4? Is it the one on your board, or if it's on the Grace Blackwell on the other board? How do you route down to that to get there? You have literally hundreds of combinations to think about to optimize this. And it might make a difference. And software will magically figure this out, right? Yes, use mVAPITch, but that means they have to come with hundreds of different optimizations to do that. Just a little example, nothing to do with network, just thinking about memory. I was playing around with unified memory in Grace Hopper. So consider these 3 loops. And it turns out 2 of them are exactly the same because you can't see the rest of the code. And one of them has 4 characters different. And assume CP means using CuPy calls and NP uses NumPy calls. And keep in mind that this level of Python abstraction is where all the AI applications are. Right, so I'm doing a 64K by 32K matrix multiply. Well, 64 by 32 times 32 by 8, right? To get a matrix multiply, I picked this because that takes 1 second on a Hopper right now. To do it in, I'm pretty sure, double precision. So I have these 3 loops. And again, the first one takes 2 seconds. The second one, 1.3 seconds. And the third one takes 1 second to do the same thing. So 2 to 1 factor, right? And the difference is, the left and middle one are the same, but I changed the allocation method and turned on the experimental managed memory support that uses the unified memory controller to move data, because in those I'm declaring the arrays on the CPU and doing the multiply on the GPU. And the last one, I just put the data in the GPU memory to start with. So that's sort of the baseline, right? But so unified memory, same code, same allocation method, but even without talking to the network, I can get a 2 to 1 difference just based on, where I put the memory, and a 70% difference based on how I move the memory through different Python mechanisms, right? So really simple test, already dramatic things. So now think about 100,000 lines of code and many libraries under this and all the different network paths and all the ways to screw that up. And then you can think about all the different communication layers. And again, all of them being built for very good reasons. All of them have different strengths and weaknesses out there. But we found a lot of ways you can do a broadcaster and all reduce. Right? You can do it through MPI and in all of its various flavors, mVAPITch being our favorite, of course. You can do it through SHMIM and all of its various flavors. There's NV-SHMIM now, if you want to do it that way. Now you can do it through NCCL, the NVIDIA Collective Communication Library, which has the sort of low-level PCI and NVLink optimizations for theirs, but you can do an NVLink broadcast, which is different than your IB broadcast, because we needed that. And now you need all of these things to work well with C, C++, Fortran, and Python, and then somebody's going to ask for Julia, and somebody's going to ask for MATLAB, and so many things, and that doesn't even get me started on the disaster that is Python package management. But of course, I'm running out of time, because always. So remember, that's just the challenges of optimizing for the network path in our exciting new world. I/O patterns, as I mentioned, look very different than they used to. Python is everywhere, and that's interesting. We have to figure out how to support inference, which you might want as a persistent service, or you might not, but it's certainly not batch scheduled like training. It might be co-scheduled for certain models doing inference. And then there's the big stuff that I haven't even touched on, like all the power and the fact that we're not going to get any more 64-bit performance improvements. where AI fits in scientific computation, the continued existence of open science in academia. The AI guys stealing all of our people and slowly strangling us by the AI behemoth that's out there. I'm actually teaching a course for the first time in 10 years because I want to understand how you teach programming in the age of AI-generated code, which gets better, dramatically better, every month right now. And to me, it seems like a great tool to use if you know how to program. But if you don't, it seems like, welcome to toddler's first flamethrower. Giving them AI-generated code and the ability to break things in these environments. And even if we manage all that, essentially, we're going to have to talk about chiplets and quantum. So we're not going to run out of stuff to do. So let me just briefly, in my last 3 minutes here, reiterate the two big themes I mentioned last year because they still need to happen, and I think there's more evidence. So one thing I talked about was we need to adapt AI hardware for science. To me, it's the new Beowulf project, right? We need to exploit the chips being made for AI that aren't going to do 64-bit well, and figure out how we're going to do general scientific computing, and we're basically not going to survive if we don't. And then we need to think about full stack efficiency for AI, because it turns out, as we have learned in HPC over the decades, that there are ways to scale up computation that don't involve just throwing billions of dollars at the problem. And our community is really good at that because we've never had billions of dollars to throw at the problem before. So, and ultimately we need to do this to save the world from some kind of bankruptcy, whether financial or carbon, take your pick. I actually just read an analysis this week that the average residential power bill in Ohio is estimated to be $15 a month higher because of all the demand from new data centers. So AI may kill us all. So why do I think we can do this? I showed some evidence last year, but we've done this before, and programmers in our community are generally pretty clever. So, in fact, without hacking by a bunch of people at mostly North Carolina, I believe to do molecular dynamics on the GPUs pre-CUDA 25 years ago, it's possible GPUs would still be languishing doing graphics processing. So that the first sort of general purpose computing for GPUs came out of the scientific community. And if we let people know that, in a couple of generations, int8 operations are going to be something like 2,000 times faster than 64-bit operations, they're going to figure some clever things out, right? Look at the Ozaki scheme that has come out that NVIDIA is now actually supporting in a library, where you can do very interesting emulation methods around FP64. By the way, if you try and Google NVIDIA and 64-bit emulation, you get a lot of stuff about how to emulate the Nintendo 64, so go take a look at that. And the AI summary is hysterical because it mixes floating point 64-bit with Nintendo emulation, so still not perfect, shall we say. But you can, if you look at a bunch of Gordon Bell's papers, particularly the 4 by David Keyes in the last few years, there's a ton of schemes that exploit mixed precision in the algorithm that let this happen. So between emulation and mixed precision algorithms, I'm pretty confident we can do some cool things and make this happen. And AI stack efficiency, I think this can be done too, because it's mostly what DeepSeek did, which gave a lot of validation to this when that came out, 6 months ago. It was nothing really earth-shattering algorithmically. It was really good code optimization and pushing well-known methods like mixture of experts out to the extremes, right? People were using 8-way compositions. They went to 256-way. But they literally just had a ton of people spend a ton of time figuring out how to optimize this stuff and got a factor of 3 to 5, right? Which, if you're spending $400 billion on infrastructure, factor 2 is pretty significant. Again, latest, like Goldman Sachs estimate is 6.7 trillion will be spent on AI infrastructure in the next 6 years. So yeah, factor 2 is worth getting. 10% is worth getting. It's worth $600 billion. And again, when dollars, we know the focus in AI has been on biggest and first. Get the biggest model out as fast as possible. And that always leaves efficiency in the dust when that's the goal. So when dollars become scarcer, or say export control rules cut off supplies of top chips, optimization has time to catch up. The hardware level microcode, software, compiler, we know that. So come explore the new systems. You can get Vista now. We have Stampede 3 with SXM H100s, and Lone Star has PCI H100s. So if you want to do fair comparisons between unified, integrated, discrete, all those systems are there. I hope we'll have our NVL72 rack little interim production system in place before SC25, and we hope we can put you on horizon with the NVL4 nodes by February, March. So come do cool stuff with them, and thanks for all you do to contribute the code, and looking forward to the rest of the day. So thank you.
We have time for several questions. Yes, please, you.
Yeah.
And great presentation. All the challenges you were showing, like the network options and unified memory, I want to get your perspective. I mean, it seems like you have been thrown a lot of compute and networking hardware at you, but from application and infrastructure standpoint, what would have made your life easier? Because clearly what you're saying is your life got really complicated.
I think the issue is this has come so fast and so furious. We haven't spent a lot of time thinking about what the optimal is, right? So like, you know, I wanted some Blackwells sooner than I can get the NVLs for. So some said, well, you can buy an NVL72 rack now. And then you look at it and this is the only configuration you can get. And I'm like, why do I have 11 network interfaces that I'm investing in? Nobody's selling them, or on the support engineer side, can actually explain that to me, other than training takes a lot of bandwidth, which is true. But how much can each chip generate and how much optimization has been done? I actually was joking to some folks last night at the dinner that you know, my real goal is to bring in that rack and just start unplugging network interfaces until something goes slower, and figure out, you know, what the right configuration would be. But again, I know what we've gone through the years to get it right with like 1 NIC per node and the possible optimizations of what stays on chip and when do you switch broadcast sizes, and you know, there's so many tricks to play. And I'm confident they haven't done all the work for all these interfaces on this architecture they cooked up 6 months ago and has been shipping for 10 weeks. But it seems like, you know, again, it's focused on spend whatever amount of money it takes to remove every possible bottleneck and hope for the best. And I just think we need sort of a thoughtful research program around how we might optimize that. And so, yeah, step one, I'm going to plug in all 11 network interfaces and then see if training runs at the same speed when I unplug 3 out of 4 on the InfiniBand and NVLink side. My guess is it's probably mostly using the NVLink and it won't even notice when I unplug half of the IBs. But I don't know that yet because there's just no data. So